Hello, so this is my entry to the Mega Favorite Numbers project. My Mega Favorite Number is a power of 2 that begins with 10 sevens. And you might ask, oh, is there even such a thing? This number is significant to me because a long time ago, long time ago now, I took a course in Budapest called Conjecture and Proof. It's a Putnam-style problem-solving course, and one of our homework problems was to determine, with proof, of course, whether or not there was such a power of two that begins with 10 sevens. And initially, this seems quite unlikely, right? If you look at powers of two, they don't even start with 1 7. If you look at the first, quite a fair number of them. But one of the things that you can do is do a brute force search, and there's actually a pretty promising candidate fairly early on. So I'm going to run a brute force search. This is going to run on my computer. So while we wait, I thought I'd mention the following question, which is, some of these videos talk about really, really big numbers, and one of the interesting things is that not every number between 0 and some of the numbers that have been mentioned in some of these videos, not every number in that range has a notation that can write it down within the physical space of our universe. So I want you to think about what does that structure look like, the set of numbers that you could write down some representation of within the physical space of our universe. So here we go. Here's our brute forced powers of 2. To save memory in the HTML, I've gotten rid of all of the ones that don't start with 7. The first power of 2 that starts with 7 is 2 to the power of 46, which is this here, and it starts with 1 7. And then after that, they tend to come in groups that are spaced 10 apart, that being because 2 to the power of 10 is 1024, so you're essentially multiplying by 1,000 almost. Of course, if it starts off with 7, it's going to wind up starting with 7 after you've multiplied by 1,000. And so we can look for patterns within this, and we see a kind of promising candidate. Here it is. At 10,962, it starts with 4 sevens. Oh, very good. And then there's this really great one at 26,399, 2 to the power of that starts with 7 sevens. Oh, so this is really quite promising. Maybe there actually is a power of 2 that starts with 10 sevens. But as we can see from this summary table here, I have the number of sevens and then the number of powers of 2 that it found that started with that number of sevens. Of course, most of them start with 0 sevens, but those aren't on the table. Quite a few of them start with 1 7. And then we get fewer and fewer. There was the one that I showed you that started with 4 sevens, and then there's the one here that starts with 7 sevens. But it's fairly clear, especially considering how long that search took, that we're going to need some sort of more advanced technique to find such a number. I want to give you a hint as to how to think about this problem. This is the hint that we were given in Budapest, and the idea is, well, okay, so I'm not quite sure about how to look at the first few digits of a number, but what about the first few digits after the decimal point? So let's solve the problem. Is there a multiple of pi whose first few digits after the decimal place are 0.777? And one of the ways of reasoning about this is modulo 1, right? So you do modular arithmetic, but not with natural numbers. You do modular arithmetic with real numbers, mod out by 1. That's essentially the same as taking the fractional part every time you do an arithmetic operation. And so what we have here is a visualization of that, right? The numbers, the fractional parts kind of form a circle when you mod out by 1. And this here is a visualization of that circle, and the target range is from 0.777 to 0.778, right? So we're looking for a multiple of pi that will wind up in that target range. It's a very small target range. We can zoom in and see. This is a very small target range here. Let's reset. There we go. Let's do some rotation. So here we enter the number that we want to rotate by, and then how many times we want to rotate by. So what this has done is it has rotated 3 times around, and then an extra 0.14159, and so on and so forth, times around the circle. And so as you can see, we wind up at 0.141, so on and so forth. If we do 2, we go 6 times around the circle, and then an extra 0.28, and so on and so forth, times around the circle, wind up here. And the question is, just like, let's go around until we find a multiple that hits the target zone. One of the things that's really interesting, if you see if we go 7 pi times around the circle, it's very close to going some integer number of times around the circle, right? An integer number of times around the circle would get us exactly back at 0. Of course, we can't do that because pi is irrational, but that's very close. And of course, I'll let you figure out what number 7 pi is very close to, what whole number 7 pi is very close to. And so what we can do is we can continue taking multiples of pi, and eventually by the pigeonhole principle we're going to get 2 that are very close together. And you can actually prove that one of those 2 is going to be 0. So these two are very close together, right? 113 pi is almost exactly 355 times around the circle. And so we are very close. This top number on the chart represents 0, and then the top line represents 0, and the bottom line represents 113 pi, which is just ever so slightly less than 0. So it's going to be some whole number, 354.99999, and so on and so forth when you do this. So what we can see here is that every time we go 113 pi times around the circle, we actually, if you ignore all of the times that we go around the circle, we wind up actually going just a little bit down, right? Just a tiny amount down, and that tiny amount is actually smaller than the width of our target interval. So let's actually go around the circle in multiples of 113 pi. And again, we go, 354.999 and so on and so forth times around the circle. And so actually we're really just going down a little bit, modulo 1. And what we can do then is do that many times and slowly work our way downward on the circle. And this is a very slow process because this is a very tiny amount that we went down by. But we can do a little bit of division and figure out how far around the circle we need to go in order to hit the target zone. And so here we go. We multiply these two numbers together, and we wind up getting that 832,245 pi falls within the target zone. And so this is some multiple of pi whose decimal digits start with 0.777. So this is what we were given in class to kind of prepare us for the is there a power of 2 that starts with 10 sevens problem. And at this point, you should probably stop the video and try to work out for yourself a proof that there is a power of 2 that starts with 10 sevens, and maybe start trying to work out on your own, if you're really ambitious, what one possible power of 2 could be. again, please try the problem on your own if you're interested. Otherwise, I'm going to move on and show you how to solve it. And the first step is to formalize the problem, right? So we need some sort of way of saying that 2 to the n, some power of 2, starts with 10 sevens. And what that means actually is that it's somewhere between, 10 sevens followed by a bunch of zeros, and 7, 9 sevens, and 8, and followed by a bunch of zeros, right? For some number of zeros. And so we can write that with this inequality here saying that, 10 sevens times 10 to the x is, so 2 to the n is between that and 10 sevens, or 9 sevens followed by an 8 times 10 to the x, right? So that's a formalization of the problem. But then we can take the log, powers of 10, so take the log base 10 of the problem, and what we wind up getting is that we're actually looking for some multiple, n times log of 2, log base 10 of 2, some multiple of log base 10 of 2, whose integer part is between the log of the 10 sevens and the log of the 9 sevens followed by an 8. Right, so that's what we're looking for. And of course, the same sort of argument, the same sort of algorithm that we did before actually still works. Because, right, the only thing that was special about pi in what we did before is the fact that pi is irrational, so we never actually make our way exactly around to 0. And the same thing works with log of 2. Log of 2, I'll let you do this. It's very nice proof that the log base 10 of 2 is irrational. There's just one slight problem. The range, our target range, right? If you actually figure out, what is the width of this target range here, it's going to be 5.6 times 10 to the negative 11 units wide. And that's really bad. It means we're going to need, 17 trillion multiples in order to guarantee that you found 2 of them that are close together by the pigeonhole principle. So, and actually computing that many multiples of log of 2 or that many powers of 2, it's just going to be awful. It's not something that a computer can handle nowadays. So let's think carefully about what it is exactly that we're looking for, right? So just like with pi, we were looking for some sort of multiples of pi that got us almost exactly to 0, and mod 1. And so what we're looking for with log 2 is some multiple of log 2 that will get us almost exactly to 0 mod 1. And so we're looking for n log 2 to be approximately equal to x. That is, log 2 is approximately equal to x over n. So really what we're looking for is rational approximations to log of 2. But we can't just go with the everybody's favorite rational approximation to log 2, which is 3/10. We can't use that. We need something much, much better. And in fact, this better approximation has to be not only good as an approximation, but it also has to be good relative to its size, relative to the numbers that show up. I had originally wanted to do something with Taylor series because they give you rational approximations, but they don't give you good rational approximations. So I just asked Sage Math. What we're doing here is we're taking the log base 2 of 10, we're rounding it, so that's what this n, we're rounding it to 1,000 digits, and then I'm looking for a nearby rational number that's within a certain range. And the way that I figured out this range, you could do this formally, but I actually just guessed and checked some various approximation qualities, and it turns out that this one works. And that's actually the way that you want to go about doing this because it means that the numbers might be smaller than they provably have to be in terms of the numerator and denominator of this rational approximation. So let's ask Sage Math, and it gives us this. This is our rational approximation to log base 10 of 2 that we're going to be using to find this power of 2 that starts with 10 sevens. So this is our rational approximation. Another way to look at that is that 2 to the power of this denominator here should be approximately equal to 10 to the power of this numerator. That's, if you rework the equations, that's what it means to be a rational approximation of log base 10 of 2. So let's do that. Let's calculate 2 to the power of the denominator, and let's figure out, let's see if we get something very close to 10 to the power of this numerator here. Oh, uh-oh. Yeah, so it turns out that these numbers that we're working with are too large to work with naturally with a lot of computer algebra software. Luckily, however, we can factor this denominator and do the exponentiation a little bit at a time. So what I'm actually going to do is I'm going to take 2 to the power of this larger factor that we've broken our denominator into, and then I'm going to round it using this n function again. Round it to 10,000 digits, so you don't think that I'm trying to trick you or anything. And then take the result and raise it to the 647th power, which is the other factor. Oh, it's done. So it gives us 1 followed by a whole bunch of zeros, which is really good, times, this is E notation, times 10 to the power of the numerator. Very good. Going back to thinking about this in terms of multiples of log base 10 of 2, right, we want it to be the case that the denominator of our fraction times log base 2 is very, very close to a whole number. It's going to be very, very close to the numerator of our rational approximation. And let's see how far off they are. They are off by 1.2 times 10 to the negative 10. So that's great. This multiple of log base 2 is extremely close to a whole number. So we've kind of looped around this many times of our circle. We've gotten almost back to 0, but not quite. We're off by, again, roughly 10 to the negative 10th. And notice that this isn't quite as much as we promised earlier, right? I said before that we really have to get 10 to the negative 11th, but it turns out that this number should work. Just trial and error got this slightly smaller number that works for this thing. So the question is, well, we have this. We know that going around the circle this many times, our denominator times log of 2 times is going to get us just this tiny little bump. It's going to be a bump up this time, tiny little bump up. And then the question is, well, how many times do we need to do that to get around into our target zone? So what we can do is we can divide the low end of the target range. It's going to be our log base 10 of 10 sevens, divided by the distance that we computed in the previous step. And that's going to give us this number here. Notice it's times 10 to the 9th. And so we need to multiply this multiple of log of 2, right? This multiple here by this number that we just calculated in order to get it into the target range, right? This is the number of tiny little steps that we need to do. Tiny little step is this here. And then this is the number of tiny little steps we need to do in order to get into the target range. So overall, the number that we need to multiply log of 2 by is the product of these two things, which is this. So that means that my mega favorite number is this, 2 to the power of
2 to the power of 458 quintillion 42 quadrillion 803 trillion 530 billion 860 million 947,692.
One of the nice things about interactives is that I don't have to read these really big numbers. You can just have the text-to-speech do that. But of course, there's a bit of an issue here, which is how could we possibly test this solution? How could we see if this number actually does start with 10 sevens? Well, we need to do a lot of really clever tricks, even just to verify this. And this is great. So what we're going to do is we're going to raise 2 to the power of this thing gradually, going factor by factor. We do one round off at the very beginning, round it to 10,000 digits, and of course you can do a little bit of error analysis to make sure that this isn't actually creating any error that would affect the final solution. And then one of the things that I also do in this formula is occasionally divide by powers of 10. Of course, dividing by powers of 10 is not going to affect the starting digits, and it's not going to affect the starting digits even if we then raise the number to further powers. So not an issue. I just do this to keep the exponent in the scientific notation that's being stored in this thing from itself causing issues in the computer algebra system. So we have to do those divisions by 10. And again, I'm raising it to this power times this power times this power. And as you can see, we get, we get 10 sevens times, this should be times 10 to the power of something, but of course we've divided out those powers of 10. So actually this answer is just going to be 7.97. Now, this is a very big number, and we can compute the number of digits, of course, by multiplying by the log base 2 of 10.
137 quintillion 884 quadrillion 623 trillion 160 billion 812 million 861,576 digits.
So this number is kind of arbitrary, but I'm nonetheless very fond of it. There are, of course, plenty of powers of 2 that start with 10 sevens, but this particular one is the one that I found, and it's such an exciting combination of having to do math and having to use a computer algebra system, pushing a computer algebra system to its limits. I can't do these really complicated computations by hand, and the computer algebra system can't handle this stuff without me doing a little bit of math on top of it. So both me doing the math and the computer algebra system doing the heavy lifting are necessary in order to find this particular number. And I just think that's great. Anytime you can make a computer algebra system like Sage Math or Mathematica weep, oh, that's a good day. So yeah, this is my favorite number. It's not particularly special in terms of standing out. It is not a unique power of 2 that starts with 10 sevens. It's not the smallest. I encourage you to try to find powers of 2 that start with 10 sevens that are smaller than the one that I have discovered here. Or maybe try to find some other technique. Maybe you'll somehow figure out how to find the smallest one. Oh my goodness, that seems ridiculous. But I encourage you to try. But anyway, this is my mega favorite number. It's important to me because it's the one that I found while I was working on this problem a long time ago in Budapest. And I hope you enjoyed that.